So we are going to talk about projectile motion today. Take some notes, projectile motion, and that's in chapter 4 of your book. Now, we talked about vectors in terms of 2 dimensions and 3 dimensions, and projectile motion is really focusing on the x and y direction. And I first just kind of want to go over like what projectile motion is, and then we really want to go through some assumptions that we make in terms of solving projectile motion problems, because we have to assume some things first for the math and our conceptual understanding to come out clean and okay. Now, projectile motion, we know is an object may move in both the x and the y direction simultaneously. So I may take my water bottle, I may not just throw it horizontally, I may not just drop it vertically, but I may actually like throw it at some angle. And if I'm throwing it at some angle, then I'm going to get some type of x and y direction, and that's going to be some type of projectile motion problem. We call it a projectile motion problem when we have an object that's moving in both the x and the y direction. Okay, let's talk about, before we do any problem on projectile motion, we first have to make some type of assumptions to make sure that the problems work out perfectly every time we do them. So one of the assumptions that we make is that acceleration is going to be constant over the range of motion. So as I throw my water bottle across the room, then I know that acceleration is going to act on it the same way at every moment of its path. We know that that acceleration is gravity, and we know that the magnitude of that gravity is 9.8 meters per second squared, and it's going to be directed downward. So we just assume that acceleration is directed downward. We assume that the magnitude is 9.8 meters per second squared. Saying this is also the same thing as saying or assuming that over that range of motion that that object is moving, we're just assuming that the Earth is flat there. And when we're doing these projectile motion problems, that's a reasonable thing to do as long as that range that that object is moving is small when it's compared to the radius of the Earth, okay? Now, we also assume, so we're first assumption is that acceleration is constant, it's gravity, it's directed downward, it has a magnitude of 9.8 meters per second squared. Second assumption is that we're just going to say that air resistance or air friction or drag is all negligible. I'm not even going to take into account of friction or of air resistance. Now, with these assumptions, as long as these 2 assumptions are in play, an object should follow, if it's in projectile motion, it should follow a parabola, should have a parabolic path to it. That parabola we call in physics simply a trajectory. Okay, so we said that we have x component here of our projectile. We're also going to have y components of our projectile because we're moving in an x and y direction. Now when I throw something, again, I'm going to throw my water bottle across the room. I'm just really mad that I just want to do these physics labs, and I'm so excited to come back, and I'm just mad, so I'm just going to get angry and throw my water bottle. Now, I know that my water bottle is going to have some type of velocity to it, because I'm giving it some type of velocity as I'm throwing it, and it's also going to have some type of acceleration, because gravity has to bring that object down, and it will. If I think about the velocity first, so let's think about velocity before we think about acceleration. If I throw an object here, here's its initial velocity, it's going to continue to move up until it reaches maximum height, because at that point, it's going to stop, and it has to change direction, because gravity has acted on it so much that now I want it to come back down towards Earth. So once I reach my maximum height, my velocity is going to start moving downward. But this isn't telling me enough. My velocity is tangent to the path for the entire trajectory. this velocity may be of use to me, but at this velocity, I need to know, well, what's it moving in the x direction and how is it moving in the y direction? So for the velocity in a projectile motion problem, you will always break them apart into your x component of velocity and your y component of velocity. So it's really important that we break these into components. So velocity, always we're going to break into a component. In terms of the velocity at maximum height, so the top of my trajectory, at the top of my parabola, my velocity has to be 0 because that object has to come to a stop to change direction to come back down towards Earth. So the velocity at its peak is always going to be 0. In terms of, let's actually just look at kind of our vector lengths here. I have my initial velocity in the x direction. Let's compare that length with this length here. These look the same size to me. Here's my other Vx, so here's my other x component for this vector. That looks the same length. Looks the same length. Looks the same length. So this picture is telling me that my horizontal or x component of velocity is constant. Why would my horizontal or my x component of velocity be constant? It's constant because there is no acceleration in the horizontal direction. The only thing that gravity is affecting is the y direction, the vertical plane. It is not doing anything in terms of the horizontal plane. So whatever my x component for velocity is here, it's going to be the same throughout the entire trajectory. And that's because there is no acceleration acting in the horizontal direction. Now your y component of velocity is different. We have acceleration that will be affecting that velocity in terms of each vector as I'm moving along the trajectory. So I can see here that I'm starting off with a pretty large magnitude here for my initial y velocity. But as I'm moving towards that maximum height, as I'm moving towards that peak, where velocity is going to be 0, where my y velocity is 0, because it has to come to a stop, so it can change direction and come back down, I see that it's getting smaller. But then as it changes direction, my Vy got a little bigger, Vy is even bigger. So as I'm going up my trajectory, my y component of velocity will become smaller until it reaches its maximum height or its peak, and it will be 0. And then as it moves back down, it's going to increase in magnitude again. So decreasing going up, 0 at maximum height, increasing coming back down. Now the perpendicular components of motion, I wrote down here, are independent of one another. And that just simply means that my x component, sorry guys, that simply means that what's happening with my x component has no effect on what's happening with my y component of velocity. What's happening with my y component of velocity isn't going to affect what's happening to my x component. So as long as they're perpendicular to one another, as long as these components are perpendicular, which they are for us, then they're independent of each other. They are not going to have any effect on one another. Okay, in terms of acceleration, if I follow my trajectory again, at every point, my acceleration will be pointed downwards, and that's because my force of gravity is always going to be interacting with that object as if it's pulling it down, towards Earth. That's my goal. So acceleration is always pointing down, and we are going to say that the magnitude of our acceleration will be 9.8 meters per second squared, unless in a question they tell you, let's just assume that g is going to be 10. So you'll see it. For us, we want to use 9.8, but sometimes don't be surprised if on a problem, and they'll tell you, just use 10 meters per second squared. And that's going to be true for the entire trajectory of any projectile and of all projectiles. So if I am thinking that, if we go back to this last slide, I said that my y component of velocity is 0, and that's because gravity is acting on it and it's slowing it down. Gravity is acting on it, it's slowing it down. I'm moving in a positive y direction, but I can see that my magnitude is getting smaller. So that means I'm slowing down. And I'm slowing down because I'm going through some type of acceleration. And I know gravity is acting on it, so that's my acceleration. So I know it's going to have to come to a stop. At maximum height, when that object comes to a stop, what's the acceleration at this point on that object? If your velocity is 0 for the y component, what would your acceleration be? I hope you don't get tricked and say 0. It would be still g. It would be 9.8 meters per second squared. Because just because my y component of velocity is 0 at maximum height, it doesn't mean like the force of gravity just all of a sudden it just stops working. It stops interacting and it stops attracting that projectile to Earth. So at every point on a trajectory, acceleration is always g. And that is a super tricky question, especially on the multiple choice of any AP Physics test. They will always ask that question. So always remember that even though your y component of velocity at the peak, at the maximum height is 0, acceleration is still 9.8 meters per second squared, or g. So I still have some type of acceleration there. Okay, we've already kind of talked about this, but maximum height is just where my projectile stops moving upward. So that's where my y component of velocity is 0. Now, we also have something that we call the range, and your range is just how far your projectile is going to move horizontally. So I started here with my water bottle, and then I got really mad and I threw it. So I wanted to know how far, I threw that water bottle. So that would be the kind of question they would ask you if they were wanting to know the range. We would ask, how far did an object move, or where did that object land from its initial point? Okay, so just to sum up again, because we kind of talked about horizontal component of velocity as well as a vertical component of velocity, but I just want to make sure we hit it home because I promise this is on your AP Physics test. Horizontal component of velocity is constant and it's not accelerated. So it's constant and there's no acceleration acting on it. It's not influenced by gravity because the horizontal component, or gravity, doesn't act in a horizontal direction. It acts in the vertical, in the y direction. So it's constant because gravity isn't influencing that horizontal direction, that horizontal component. If I didn't have gravity, if I shoot this cannon out, if I shoot this cannonball out of a cannon here, and I didn't have gravity, it's just going to continue to move in a straight path forever and ever and ever until it comes in contact with something else. So it's just going to stay constant. It's just going to keep moving. But because I have gravity, I get some type of y component in there with its velocity. So horizontal component, constant, no acceleration there. It is not influenced by gravity. It will follow this following equation. So if I'm ever trying to find the velocity for a horizontal component, or maybe I'm just trying to find like the position, whether it be final or initial, from the horizontal component of velocity, we use this. Now where did I get that equation from? That is one of your fantastic kinematic equations. Specifically, we could have x equals xi plus my initial velocity times time plus 1/2 at squared. That was one of my kinematics that we learned before. Let's say that we started at the origin, meaning that my initial x value, or my initial position, is just going to be 0. And I know that my initial velocity in the x direction, I have some type of constant velocity there, times my time. Then I have this plus 1/2 at squared. Well, we just said that the velocity in the x component was not accelerating. The velocity was constant. So if it's not accelerating, acceleration in the x direction must be 0, because my velocity is constant. So it can't have an acceleration there. So then that means if this is 0, the whole thing is 0. So my x must be just that initial velocity in the x direction times time. And that's where I get that from. Okay, if we look at the vertical component of velocity, we know that it is undergoing some type of accelerated motion. And it's undergoing some type of accelerated motion because gravity is acting on it. It is accelerated by gravity, 9.8 meters per second squared. We know it's also directed in a downward direction. Now we have not just one equation here, but there are a couple different equations that we could find the vertical component of velocity, and I have all of those listed here. They're a little different than, there's a few little variations here, and there's some variations because instead of saying acceleration, instead of writing A, we just substituted that with G, because we know that the acceleration in the y direction is 9.8 meters per second squared. The other thing that changed, so G is something new in our kinematics. The other difference is I have these minus signs. That's because gravity is directed downward. So it's going to be a negative G. I'm minus G. So my gravity is directed downward. I need to account for that in my kinematic equations. And we do that by just saying minus GT, minus 1/2 GT squared, minus 2G y minus, or the displacement of y. Okay, again, I think we talked about this, but let's just reiterate. Acceleration at the highest point. The vertical velocity and the y component, or the vertical, y component of velocity, or vertical velocity, is 0 at the top, because that's to stop and change direction, because gravity is accelerating it in the downward direction. What is the acceleration at the top of the trajectory, or maximum height? We said before, that is 9.8, because acceleration doesn't just turn off all of a sudden when my velocity becomes 0. Okay, when we are analyzing projectile motion, when we are analyzing projectile motion problems, we want to consider, again, x and y components, x and y directions. Now we know that the actual position at any time is given by my kinematic equation there. So this RF, RI, that can be my x direction, that can be in my y direction. So I have to account for x and y when I'm trying to solve for the position. So I can't just do RF, RI. Instead, I'm always going to have to break it into x equals this, and then the same thing for y. That'll be minus 1/2 GT squared. Okay, initial velocity can be expressed in terms of its components. So we can say that I know that my initial x velocity is going to be the cosine. My initial y velocity is always going to be that velocity times sine. So if we go back to if here are my triangles here, let's say that my x was just up here, I would see that my adjacent would be here, so x has to be cosine, my opposite would be y, that would be my sine. So I would always want to make sure, and we will just always know that y is sine and x is cosine. Okay. The x direction has constant velocity, so the acceleration in the x direction will always be 0. And the y direction is in free fall, and that gravity will always be directed downward. So my acceleration in the y direction will always be negative g. And that was part of these assumptions too that we were kind of talking about at the beginning. We're just elaborating on them more. In terms of final position, our final position, we can see this as a vector sum of several things. It's a vector sum of the initial position and then the position resulting in initial velocity and then position resulting from the acceleration. So I can see all of that here in my vector diagram. We can also calculate range and maximum height. These are two very, very specific questions that our AP Physics test will ask. They love asking, can you calculate the range or can you calculate maximum height? And we know that range is just horizontal distance of the projectile, so how far did that projectile or object move? And then maximum height is just that peak position at the projectile, which we can just call that h. Range we'll just call r. Now these have specific equations with them. These specific equations as well will not be given to you on your AP Physics formula page whenever you get to do your free response questions. So you should know these two equations very, very, very well. So just in case they ask you something, and there's lots of multiple choice questions that will ask you about height or range, and it's very helpful to know this equation to answer the questions that they ask. So the height of a projectile we can find by using this equation here. Height is equal to my initial velocity squared times sine squared theta, and then over 2 times that acceleration due to gravity. Your range of a projectile is similar, but it can be solved. Range, or r, is equal to my initial velocity squared times sine 2 theta over just the acceleration due to gravity. And one of these we're going to derive here in just a second. Okay, so range of a projectile. What is the best angle that I could project something at to make it go the farthest? That would be 45 degrees. 45 degrees would be my maximum angle that I would get the longest range. Now, if I see here 75 degrees and 15 degrees are going to land me in the same spot. And it says here, complementary values of the initial angle theta are going to result in that same value of r. So I'm working with perpendicular components, so as long as they're going to add up to 90 degrees, those complementary values, I'm going to get the same range. So there is a difference, though, in terms of height that I can see here, and then also what I would call time of flight, how long that object is going to be projected in the air. Now, 60 degrees and 30 degrees, those are complementary. That will get me a little bit farther than 75 and 15. And then I can see that 45 degrees is going to give me my maximum range. So to sum that up, maximum range occurs at 45 degrees. Complementary angles, so 75 and 15, 60 and 30, they'll produce the same range, but maximum height is different, and the amount of time that it will be in the air is different. So maximum height for that 75 degree is going to be way larger than my one for 15. Same time for time of flight. Okay, so we know that, or we assume that and we also see every day, when I have an object in projectile motion, then we have seen that it follows a parabola. It has some type of parabolic path to it. Now, a parabola, if I think about the equation for a parabola in standard form, it is, make sure I write this, it's too high. In standard form, a parabola is y equals ax squared. Let me erase that, guys, sorry. Ax squared plus bx plus c. Well, I want us to show that using x and y components together that our components actually really do follow a parabola. We can derive that my projectile motion or my projectile will follow a parabola. Okay, so I know that first I just want to choose to start off with, we're just going to start at the origin. So I'm just going to say we begin at origin. My goal is to try to show projectile motion has this type of equation, this type of form, just like a standard form for the parabola. In the x direction, we said x equals and we know that in the x direction, we said that we're beginning at the origin. So xi is going to be 0. I first want to just look at my components to try to get it to be y equals some function of x. So xi, my initial position, we're calling that the origin, so it's going to be 0. I know that a projectile is always going to have some type of, oh, that should be times t, sorry guys. My projectile is going to have some type of horizontal constant velocity, so I'm going to just leave that, bring that down. My initial velocity in the x direction times time. And we said before that the acceleration in the x direction is 0 because gravity isn't affecting that x component of velocity. So I can just say that that's 0. So we said this before, x equals simply that initial x velocity times time. Okay, let's do the same thing for y. So I did this for x, but now I want to do the exact same thing for y. For y, we know that y equals my initial y position plus the velocity, that initial velocity in the y direction times time. And then we know that the acceleration is gravity, so I'm going to say minus 1/2 gt squared. Okay, again we said we started at the origin. So that means that my initial y position is 0. Now, I also have my initial position in the y direction, or I'm sorry, my initial velocity in the y direction times time minus 1/2 gt squared. And I can't cancel or I can't disregard my acceleration in this point because we know in the y direction that acceleration due to gravity is what's keeping it going. So I want to show that this will have a parabolic path y as a function of x. Now, I see that time is in both of my directions here. So to make this simple, I want to rearrange this for time. If I rearrange that for time, I'm going to get time is equal to x over that initial, my initial velocity in the x direction. Now that I know this, I can plug in t equals, let's write it over here, x over that initial velocity in the x direction. I can plug in at every time here my x over vix, so that way I can get y as a function of x. I'm trying to show that this follows that standard form for a parabola. So let's do that now. I would get y equals my initial velocity in the y direction times the position of x over that initial velocity in the x direction minus 1/2 g, and then I want to write again my t, which is x position over my initial velocity in the x direction, and that's squared. So now I just want to like simplify this, and I want to pull those x's out because I want it to try to look like this equation here. So let's rearrange this stuff. So I have y equals, I have VI y over VIX times x here. So I just have this over this times x minus, I have 1/2 g, I want to pull that x out. So if we squared those things, I would end up getting g minus g over 2 VIX squared times x squared. Okay, so let's compare my parabola has standard form ax squared plus bx plus c. And I just found that y is a function of x for any projectile object based on my kinematic equations is y equals a negative g 2vx times x squared. So here's my a times x squared plus, then I had my initial velocity in the y direction over my initial velocity in the x direction times x. And then my c in this case is just going to be 0. So this, using kinematic equations and saying that y is a function of x, I can derive that a projectile will follow a parabolic path. Okay, so